Hello, welcome to you all. Sorry for the noise in the background. That's the noise of the FPGA we are going to work now. The FPGA that we are going to work today is going to be ZCU102 evolution board. What I'm trying to do is just to briefly explain the whole steps involved. If you want to build a project and then make a bit file of it, and you want it to be implemented on your hardware, that's your ZCU102 board. That's what I'm having here. So for that, as we all know that we have to go for the Vivado. I'm just turning on the Vivado Enterprise, because if you have to work ZCU102 board, it has the port XZCU9AG. So this XZCU9AG is not supported in the Webpack or the free licenses. So you must have that enterprise license that we are going to work now. Okay, so we have opened the Vivado. I'm going to create a new project, and for the new project, the basic settings, the name is project 2. You can change the project name as well. I'm going for the RTL project, which will enable me to add sources, design IP integrations, and RTL analysis, synthesis, implementation, design planning. This is the whole steps involved whenever you design architecture on your FPGA, and you want your FPGA to behave like that using the resources of your FPGA. So it's a big thing that you have to cover. That's why I have kept it to a very basic example. So by keeping it to a very basic example, I will just give you an overlook at what you can analyze from it. Okay, going next, for the first is the add source file. Add source file is the file that you want to add. You have two options for this very low VHDL file, whichever suits you, or a simulator language based on the language you suit, or you can go with the mixed as well. So I'm going with VHDL and a mixed. So I'm going to add and create a file, and I will just give this name. For example, I'm going to give this name OR. It's going to be OR gate implementation on the logic gate. Or okay, so just OR logic gate implementation, which is going to be transformed on the FPGA code. Or let's say not go with OR, we will go with AND. Okay, let's go. Okay. So we have our VHDL file, and we will go next. We have created this file. The next file required is going to be add constants file. Add constant file is important because it's going to link your hardware pins to the pins needed for the the pins that you are going to connect your created model with. Like you will be defining that the schematic that you have defined which pin you are directing of the FPGA in hardware. That's ZCU102 I am having. You can have the others as well, but that's the pins that I'm going to connect from here to there. Okay, so just for the pin information, what you can have a look is that I have just kept a basic of the image. This is the image of that switches, and there are their pin names and the LEDs that I'm going to connect and use. So for this we need that, so that's why we are adding the constant file. So we are going to create it. We are going to name it AND because we are using AND. Okay, and yeah, so next, now this is the phase. You should have the license of, if you're working on Vivado or whatever you are, but the port or the board you are working on should be supported by your license. So I will search, because I have ZCU102. I will just search ZCU102. ZCU102. I have this evolution board, and it's installed. I will give it the next setup. You can easily look for this part here, the FPGA part, that is XZCU9AG. It's supported by this license. That's why I will be able to build all the bit file and every stuff. So that's finished with the initialization. We will go with the project inside, and this is the entity name. That's and it's behavioral. You can change it to anything. I will just write data flow. And for AND gate, because we are designing AND gate, we know that we have two inputs and one in, one output. So just for the output I'm keeping it A, B and X. A, B are the inputs and B is going to be the output, and this is the MSB and LSB pins. If you want to use like 32-bit, 64-bit, 4-bit AND gate or 5-bit AND gate, you can select the bus and you can define the MSBs and LSBs. So far I'm just going with the single bit, so I'm not doing anything with the buses. So that's updating, that's creating. It's going to show a syntax error. I will just show you why the syntax error is. If you see, we have given the name AND here. So basically the problem is that AND is the another function in Vivado, so I'm just going to give it AND logic, and I will try to AND it here as well with AND logic. So just okay, here as well, AND logic. Okay, so this was the errors that I have sorted out. Hopefully the syntax error file is going to be removed, and this is going to be updating. So updating, and the design should be converted to a triangular project file. Yeah, triangle file. This is design that basically represent that this is the file we are having. So because of initialization we have A, B and X, and what I'm going to define in the architecture is I want to take this X should be updated, and this is the syntax of updating the X. And what I'm trying to do, because we are trying A and B, so it's not sensitive, so you can just go with and B and semicolon. That's it, because of the easiest implementation. So let's see, I just saved it, there is no syntax error in it. So before going to any synthesis, because this, if you see here, this is the run simulation, where you actually test your system that either it's working well or not. Then there is the RTL analysis, you see the logic diagram of your gate, and then you synthesize it. After here it's the basically conversion towards the hardware or the HDLs with a bit file. So running a synthesis and then implementing that synthesis and then finally generating a bit file that you are going to put on the hardware. Okay. Okay, so what we are having now is we are going to run this run simulation with run behavioral simulation. Let's see how our this architecture is going to be. So far we haven't given any values to A, B and X, so these are the bogus values. I will just go to time 0. Okay, okay, and here I'm just going to give them the random force clock values. Clock values can be leading value 1, it can be 0. After time, like you say 500 for example nanoseconds, you can change any to anything, and 100 nanoseconds and duty cycle, so you can change the duty cycle as well, or you can change the period as well. Okay, so this is the for A. For B I will try to keep the same, 1 for edge leading, 0 for trailing. After time offset same as that was my 500 nanoseconds, and let's say give it 25 duty cycle long. Let's see how what happens. Okay, and this is what happened now. So I have A and B. I'm going to run it now from here. Sorry. So yeah. Okay, so if you just minimize it, hopefully you will be able to see the logics of AND that you can verify. So if you see here, A and B, these are the inputs. That's 1 0 1 0 with a 50% of duty cycle, and then 25% of wind cycle with 1 and 0, then 1 and then 0 and 1. So what we are performing here is AND gate, and is 1 1 and output is 1. So this simulation is verifying that we are having the correct things. So you can generate the schematic or data flow design. You can just click on the schematics, it will liberate the design and create a reading netlist. This video is going to be a bit long. Some steps takes the steps. So this is your AND gate that you have just implemented now, so you can easily see the RTL schematic of that as well. Sometimes if you will be having the block, and it will involve multiple AND gates and OR gates, so you can double click on it and you can see the exact things. So now the actual things start from the running synthesis. So I'm just going for the synthesis, launching with the number of jobs to give, and always see here this shows that what is happening, and either the things are ready or not, or what the synthesis is, and how the synthesis design is going to be used. So we'll wait for a while. Bear with me, because sometimes we have to wait, and we have to rely on the system and being just recording in a flow and not pausing it. Yeah. Running synthesis designer. Okay, so we are done with that. So before I go to the run implementation, I have to show, because we haven't given any constants. So if you have constants given in the file, so you can give it that to this, but for me, because I haven't given any synthesis, any implementation, so I'm going to open this synthesized design to see what our design is going to look like. Okay, so this is the design of the FPGA ZCU102. You can have the pin ports and the configuration for that. For example, we haven't given anything here. So now the exact hardware things comes up, because these are the pins of the FPGA, and these are the pins of the FPGA, which are basically labeled with rows and columns that we have to go and we can give to the specific thing. So with the simulation things we are done. Now we are heading toward the hardware side. Sometimes if you feel that you are missing with this device constant file here, or you are unable to identify this input output ports, you can easily go to this this layout here, and it's going to be input output planning. So if you just click on this input output planning, it will just lead you here where you can go with your device. So this is your device on an FPGA, and this is your package, and you are going to define that which key I'm going to use. Okay, so how to decide it, I will just show you how we can decide that which pins we have to use. So as I said earlier, that we are going to use this switch 13 SW13 and these LEDs. If you see this LEDs, you can select any one. I will go with DS37, but these are the labels on the board, the FPGA ZCU102 board, right? But for checking it, what exactly pin its label, because if you see here, there is nothing that you can identify as SW. Okay, so what we have to do is we have to make a combination of these things. So for this we have to go to the file of ZCU102. So I will just go and okay, remember this SW113 starting from 0 to 7. Okay, and these are the LEDs 38 to S44. So here is a file on the Xilinx, which is ZCU Evolution Board User Guide. So before you are proceeding to the FPGA board, what I would suggest you that here is the power connector where you are going to power connect it. But before power connecting it, what we need, because when we need to program the FPGA, there are two things, that you can use the FPGA, the architecture that you are designing, and the second is that you can go with the existing image of Linux, or you can say Pink Linux, which is installed in this ARM controller. So on this FPGA development board, you have the ARM processor, as well as you have the sorry for that. Okay, no, okay, we have a processor on it, and we can build the FPGA, our custom FPGA on it. So for that, there is the mode that we have to select. So if you, okay, I have it in the second file, I think. Yeah, so so for the mode, we have a dip switch SW6 configuration option for the switch. So here you see this is the switch that you can find as a SW6 switch mode. These are the 4 buttons which exactly define which mode you are going in. So we have currently these 3 pins here, the 3 combination that we can use. But the important thing is that whenever you are configuring or you are loading from the SD card, you go with the settings 110, and if you are JTAG means we are going to configure it, program our as FPGA board with the code that we have just written, like for the AND gate. We are going to use our FPGA as an AND gate. So this is the JTAG. For this we have to do 000, but the important things come here. For this dip switch, in relation to the arrow on the switch moving the switch towards the label on is a 0. So if you want to do JTAG, all the 4 pins should go towards on level. Okay, so where is the on level, you will easily identify here. So currently you see only 1 is here and 3 are here. It means it is leading to the SD card, because this 0 represents the first pin towards on and the rest are towards the other end. So before heading to that, we have to change the mode, and I would ask you to do not turn your board before doing this, because we have to do the settings, and then we have to turn it on. So I will let you know when we have to on. These are the settings when we are doing the settings on FPGA is powered off. Okay, so these are the 4 pins that should be going up for the mode that we are going to we want our FPGA to be active for the programming, that we can program it. Okay, now let's come back to the switches and LEDs. For these switches and LEDs, we have to define that which 2 switches we are going to use and which LED we are going to use to program it, right? So for this we have this here, and another thing is when you are programming, you have to connect the USB-C cable with your computer to this JTAG. Okay, if you are programming it, and if you are using it as a processor and you want a serial communication with that to use that processing and the image in that, so you will be using this UART. So we are now programming our FPGA, so we will be JTAGing it here. So we are going to use this port which is called JTAG. Okay, okay, now coming back to these LEDs, the switches, and this, let's see if we can find it out. So we have that switch 13. Yeah, we have this switch 13. So let's see and have a look to the, before that we will go for the LEDs. We had 37 to 44. So yeah, so before I had to these all things, what are the important here? These are the LEDs that you can use. I said that I'm going to use 37. You can select any of the LED here. For D37, it's going to be the output. Okay, 37 is the pin, if you see here. So yeah, this is the 37 LED which I'm using. Okay, but we can't give 37. So for that, what we have to give AF13. So we will go to Vivado. So we have this AF, and yeah, this is 13. Okay, this is the pin of the LED that we are going to give. So this is AF13. But how to give it? So we are using it as an output. So this is the package pin we have to select. Yeah, okay, I was wondering why it's not working. Okay, correct me if it was AF13. I will have a look to that again as well. But AF13. Okay, we have AF13. The next important thing is input output standard. So I'm selecting LVCMOS 33 because the LEDs and the switches we need 3.3 volts, and these things that you can find from here as well. It's mentioned here as well that we are using LVC and CMOS. So this is the thing which I used, and this is AF13 which is used. So things are going to be displayed on this DS37. Okay, so let's go for the inputs. So we have these switches, that is SW13. Okay, these are the switches. You can use any of the switch from here. Again, they are going to be input output standards of LVCMOS 33 means 3.3 volts. So let's say I'm going to use 13.1 and 13.2 means AK13 and AL13. Okay, so AK13 and AL13. So this is AK13 and this is going to be AL13. Okay, AL13. So if you see, it highlights this pin as well, it highlights this pin as well, it highlights this as well. So I have selected these 3 pins I'm mentioning here. If you see this white block, Yeah, it moves. If you select here, it's at A13, the AL13, and this is at AK13, and this is at AF13. These are the 3 pins on the FPGA hardware that we have selected on the synthesis design. Like, this is the architecture of that. So yeah, we have to do this as well. LVC mos 13, LVC mos 33, sorry, 33, yeah, which mentions VCCO of 3.3 volts. Okay, so we are done with it. We are going to save it, saving the current, okay, this and that. Okay, so remember we created an NXDC file, so I'm just going to update that with this. Okay, we updated this, so we have we are going to synthesize our model now. I think we synthesize, yeah, we synthesize it, right, because it shows synthesize is complete. So the next step is you can see different things and how it's having, how is the schematic and how the other things are, how the report power and the other things are. You can check different steps from here. So now I'm going to run the implementation. Okay, so the things are happening. Initial design cancel is here. This is our HD design, and this is that. This is the package we are working on, and this is the device. So running OPT design and implementation. Once the implementation is done, implementation means we have synthesized the model and it's going to convert this to a bit file. So after that we have to generate the bit file, and we have to load that bit file into our program, like uploading it or downloading into the FPGA. We will be waiting for a couple of minutes. It will take a bit of time. That's why I've selected the smallest example, that it should not take much of time. Okay, we are done with that. So now the next step is we can open this open implementation design. So this is going to open the implementation design here. So that's the implementation design that you can see and verify. So just next to it is going to be because we have done with the implementation, we can do different stuff, we can check different things. Again going with the schematics. So if you go with this schematic now, this is going to be the real implementation on your FPGA board. So if you look this, you'll be able to identify that what exactly these things are doing and what is going to be the output. So AB is the input and this is the output, and these are the things that are exactly happening now. Okay, so we are done with the implementation, synthesis. Remember, we will be going exactly with the same. So now we are going to generate the bitstream file. Bit file is the file which we actually download into the FPGA, and on the basis of that bit file or a bitstream, the FPGA runs. There are other implementation, other things as well. So running right bitstream, so it's bitstreaming now. So these reports which I was mentioning here, I will just come back to that as well. It's basically explain how much resources of the FPGA you used, how much are the left, how was the power utilization, and the other stuffs. Okay. So we selected that LED, and we are going to run this now. Okay, so you can generate the report as well, or things as well. Okay, if you want to see for the reports, so these are the different synthesis and things report. Yeah, it's just a summary. You have to click on this and find out the reports for each. Okay, like these are the reports for each. Okay. Yeah, there's going to be summary as well. I will show you that as well, hopefully. So now we're done and we are exactly at the end now. We are passed through all the tests, so we don't have any target here now. So what we are going to do, we are going to open target. So auto connect means it's going to connect our thing with the FPGA, right? So for that what is important, that as I mentioned right here, I think I'll just go quickly at the top to show you that what we are going to do now. So remember, we changed this switch. Let me find out this switch. Yeah, this one 26 to all zeros for the JTAG, and we are connecting this JTAG with JTAG with our USB cable, and then the USB cable with our system, right? So for that, what you have to do, you can open target if it's not accessing it. So you can open target because I have connected it earlier as well, so it may recognize it ahead, but you can auto connect it. Okay, I will just connect this here, and I will go with the open connecting. So if you see, it shows no hardware connection or no connection. Now it's auto connecting it. So yeah, it's the possibility that you see different errors. If you see any error here, okay, like it can be the error related to that the PL power is down or non-startup. So these 2 or 3 errors might be due to the switch mode setup, this 26 mode setup, which I have just placed here as well. So if there is going to be any problem with the mode, it depends on the board, right? I am using ZCU102, so for this this is the combination, and this is the combination for the other thing. So now if the combination is not going to be similar like this, so the error may pop up. Okay, so if you pop up with those error when you connect your device, so that may be the problem, so you have to go and have a look to this. Okay, I'll just refresh this device. So if you see, it has found XCZU9, which is the part name of the ZCU board. Okay, so now the last thing left is we are having everything here. We are going to program our device. We are going to click it. We have loaded this logic file. If it has not get here, or you have saved it somewhere else, so you have to load it like this. Okay, now we are programming our FPGA, and it's processing 15, 23, and 26, and 23 and 36, and the percentage is going on. It means this program is actually programming our FPGA. So yeah, we can quickly test this FPGA and that what we did, and how it's actually performing. So yeah, this is the whole thing which involved all the things and everything involved in that. Okay, so we have few reports, we have this and that. You can do different stuffs here. There are different things basically which identify different report, different simulations. Yeah, for everything you can add. There's one other thing, that add configuration memory device. These are the other perspective. We are not going to go on that. Yeah, so you can create these things and that. I'm not going into the depth of that, so you can go into your project summary. So this is the project 2. This is what you have created with the board which you are using. You have completed with the synthesize. There was a 1 warning and 3 warning. I just haven't used it. So it's just showing that how percent LUTs you have used, look tables, on-chip power, utilization, and the reaction temperature, thermal margin, and the other aspects. This is just a summary. By clicking on different things, post implementation and post synthesis, these are the 2 different things. So that's it from my side. Thank you so much. Thanks for watching.